Okay, so good evening, everybody. I hope I hope you're fine. So I'm Xavier Dupré. As now there is no mystery about that. I'm working for Microsoft. I'm also a teacher at the NSAE, and everything is related to machine learning. So I do machine learning every day. I teach machine learning every week. I don't dream about machine learning every night, but everything is connected. And just to start and to have an idea of how, I would say, how close you are to machine learning, who knows scikit-learn, who? Okay, and who? Okay, so half of it. And Python? Okay, it's not a snake, if everybody wants to ask, just to precise. The plan of tonight is, so I'm going to talk about ONNX, which is a way to deploy a model. So ONNX is just a name, but behind that name you will find other names, but because ONNX is just one component. And I'll start about why today we use open source. So it's not, I would say, the truth, it's my interpretation, but it's also a way to say, okay, now, for the first time in my life, I only do open source. So everything I do every day is on GitHub. It could be for my teaching, could be for Microsoft, but everything is on GitHub. And that's, I never thought about that day. 20 years ago, I was training some model to learn to recognize unwritten words on images, and everything I did was for my company, so it was private. And now everything I do is public. So I think it's a change. And when I started, I was basically not doing machine learning. It was called statistics. But basically, I won't say it's the same, but the French translation of machine learning is apprentissage statistique. So you know it's not very far. And okay, you can say now it's a new name for the same thing. Okay. For very expert, I think they would say, okay, that's the same thing, same theory there. Behind, every time you need to, you have an algorithm, you need to show it converges towards something. But at the end, it's all about optimization and statistics. And when I left my school in 2000, something like that, I was learning R. There was no Python. I was learning SAS. Nobody knows SAS. Wow. And somehow MATLAB, something like that. So everything was quite expensive. I don't remember the price of MATLAB now, but it's at that time it was okay. Can you lend me your copy you have about MATLAB, because I have some project to do and I don't want to pay for it. And so the school was giving us some MATLAB stuff we could use later, but it's not very agile. In 2000, I was working on my PhD, and I was trying to recognize words in images. Basically, I was spending most of my time implementing an idea I could have in 5 minutes. So I was playing with C++, and I was dealing at the same time with experiments, how to find the best model, deployment, how to make the customer use that model the faster it could be. So I was everywhere, at the conception and at the deployment. And there was nobody to do that but me. So you had to do experiments, you had to optimize your model to find the best one, and you had to plug it into the software you were selling to a bank, or, well, at the time it was a bank. So, and really, I never sold a machine learning software. I don't know if you did, but in my life, I never sold one. I implemented all my life machine learning software, but I sold a software able to do handwriting recognition. Now I sell software able to train models. No, I work on that, but I don't sell it. Basically, it's a machine learning library is a very it's a product very difficult to sell. It's too complex. The person implementing it is as skilled as the person using it. So you cannot sell it. It's too... the real value is very difficult to explain, except if you are an expert. Just to come back to the previous slide, during that time I was working on my PhD, but I was doing some, I was teaching first in C++ and Python. So I'm doing Python since 2005, which is very close compared to many people. And I discovered MapReduce in 2008 with Yahoo. And in 2014, we opened, I think it's the beginning of every school now has a master with about data science. Previously it was statistics, but now it's data science everywhere. You can check, it's everywhere. What happened in 2012? Deep learning, I think. It changed something. So you can see trends on Google Trends. So in 2012, something is happening. Apparently, McKinsey saw it a year before. Say, okay, we are going to need data scientists a lot. And when I say a lot, it means a lot. And you're here today, so I think that prediction was true. In 2012, you had a version of scikit 0.12, not really usable, or maybe nobody knew it, but it was the first draft of something very popular now. And deep learning, for the first time, won the competition ImageNet, which means how to recognize something in images, thousands, millions of images. And since that day, deep learning always wins that competition. After that, we realized that deep learning is quite complex. So it's difficult to have, it needs GPU. And basically, when you hire somebody to manipulate data, he doesn't have time to play with the data and play with GPU. GPU is, okay. Does somebody try to play with GPU and C++? So 4 people. You were 40 to use scikit-learn, and now you're 4 people to play with GPU. So that's the ratio. And it's quite hard. You can lose some hair by just doing it, so believe me. So we started to have 2 different paths, data scientists and engineers. You still have PhD students who know to do practically everything, they're bulletproof, but nobody wants to do a PhD, and it's quite, well, 5 years ago doing a PhD was quite not very popular, and you had to accept some, I would say, loss in salary. Okay, just a silence, but I think now it's a lot better. But basically, either you're a PhD student or data scientist or an engineer, and now you have to choose. You cannot do both. Mostly because when you try now to optimize an algorithm, you're going to optimize it for machine learning, try to find the best performance, choose the best model, and you're going to learn some expertise, and you're going to use some libraries tuned. But when I say tuned, it's tuned by very skilled engineers for very specific technologies, GPU, TPU, you have many of them. And if you want to hire somebody, you're going to precise. You don't want somebody skilled. You're going to need a data scientist or an engineer. And they're different person. So open source, I would say now is a necessity. Because, as I explained, nobody is able to sell a machine learning library as it is. And now we need some very high performance, and it's, I would say, very high investment. If you want to build your own GPU library, let's say if you want to build TensorFlow from scratch, how much time do you need? A year, 2 years to get the same performance? How much? It's difficult. And if, let's say, Google keeps it private and wants to sell you TensorFlow, you say, okay, but it's very, the price is very high. How much can I get from it? It's difficult to say. TensorFlow was started 10 years ago, I don't remember. And now, after it took 5, 6 years to, I would say, be recognized, to bring value, and to be used on an everyday life. So it takes some time. So open source is here to say, okay, let's share what we did. Let's build complex products, because there is no other way to build them. You also have internet, GitHub, so many tools came together to bring, I would say, to create that value, open source software, and very specialized. And you can see Microsoft is not the last one to do it. I think we have one of the biggest repo on GitHub before we bought it. So why deploying a model? As I said, we need performance. I'm just going to tell a story on Bing. And I used to work on Bing a couple of years ago. And on my daily life, I was first trying to mine the logs and see how to improve Bing, the search engine. So basically, MapReduce every day. You mine queries. You submit MapReduce job. Today with Spark, 5 years ago with Cosmos. After you mine the log, you try to train a model, you try to extract features, and you train something, you build something. And now it's done. You have a model able to predict, for example, if a query is adult, because you don't want to show adult result to non-adult users. You want to predict if the query is local. And once it's ready, you have to use it on the search engine. And you have a few milliseconds to get your results and to use them, a few milliseconds, which means you have to be very efficient. And basically, what we were doing, we had two implementations, one to do experiment and another one to predict for Bing. It took time, because every time we had a new model, you had to update the implementation on the search engine, which means the same model, the same experiment, ended up by implementing twice or 3 times the same algorithm, prediction algorithm. So yesterday, what I was basically doing, I was doing some feature engineering, training model. In the best case, I was implementing only twice the same model, the same prediction algorithm, because we started to automate some part of it. And in the worst case, I was implementing 3 times the same algorithm. One, because I needed to train my model. The second time, because I wanted to use it on a cluster, a Spark cluster, for example. And the last one, in the web service. And I were constantly switching from C#, Python to C++. So you had to be very agile. If I take an experiment, you have the first part, feature engineering, and this one was implemented three times. And the second one, the model itself, was implementing only once, and after we had to convert the model into something usable, C# or C++. So that's what we were doing 4 or 5 years ago. What we want to do now is to shorten the cycle. You train a model, you deploy as fast as it takes to press a button. And the difference is, when you train a model, you have to be very efficient when you compute lots of predictions, a batch of predictions. When you plug your model into a web service, you have to be very fast to predict one time. The customer goes to your service. You want to predict something about him. So you want to predict one time, and you have to be very fast. And it means usually you don't have the same optimization. So cycle, you train somewhere on your laptop on a very powerful machine, and you predict somewhere else, and you want to minimize the cost by when you switch. ONNX. So that's a solution we propose. You have three elements. And basically, the equation you want to solve is you train in Python, but Python is very slow. You want to use your model somewhere else, and you want to implement it in C++. You can train with GPU, but when you have a web service, it could be CPU only, not GPU. You want to train here on my machine, but it's going to be deployed remotely. And you don't want to implement. Believe me, it's lots of bugs. You don't want to do twice the same thing. So before, I would say a couple of years ago, you needed somebody very skilled. I would say full stack engineer. When you see that, it's somebody able to do that in a couple of weeks. But we want to be faster, and we don't, and for everybody. Make it available for everybody. The first, so ONNX is, I would say it's a concept, and this concept has three components. The first one is when you have a model, you need to describe it. So by describing it, I mean Randomforest, everybody knows what it is. But if I had feature engineering, you're going to have your own feature engineering. And what changed, I would say, from back to a couple of 3-4 years ago, it means you have libraries, for example, with scikit-learns, and your first instinct is to try whatever is available. So, and usually it works. You have a pipeline in scikit-learns, and you reuse the components, and you can describe your model as a pipeline. Okay, that's fine. And with ONNX, we're going to first convert this pipeline into an ONNX description. First, ONNX has, I would say, made a list of useful functions, matrix computation function. So you have everything about matrices. So that's the first part here. And second part, you have new functions, machine learning function. And that's it. Basically, your pipeline, your model is going to be described as a patchwork of this. And I don't know if you can cover all the models you have, but I think in scikit-learn, the plan is to cover whatever scikit-learn has. Second component, once you have your model in scikit-learn, you want to basically describe it with ONNX. You're not going to do it yourself. Right now I'm working on a converter which takes a scikit-learn pipeline and describes it with ONNX. The same exists for Keras, PyTorch. Basically everybody is trying except TensorFlow. You have ONNX converter from TensorFlow to ONNX, but I'm not sure Google does it. I think it's other contributors. The last part is, once we have described a machine learning model into ONNX, we want to use it to predict. And that's the last part needed, a backend or a runtime. So in Microsoft, I contribute to another open source software, which is ONNX runtime. And this runtime is able to take any ONNX and to compute the prediction. And it's working on Windows, Linux, ARM, ARM. I don't know how you say it in English, but it was first started to compute prediction for deep learning. And we thought that that would be great to extend it to standard machine learning. The runtime, more about it, it's implementing C++ to be fast. It can be used from Python, C, or C# through wrappers. You have a CPU implementation for everything, and you have a GPU implementation for deep learning. So you have two versions of the same runtime for GPU and CPU for deep learning. The goal is to use deep learning somewhere where you don't have GPU, so on your phone or on just a machine you use to run a web service. Everything is on GitHub, and the license is in MIT, so everybody is free to contribute. Well, if you want. I'm waiting for you. So now I've described ONNX. The plan is to, well, if you want to use it on your daily life and deploy your model with it, you train a model, you convert it to ONNX, and then you take your file, and you copy it wherever you need to run it with the runtime. And basically, once the runtime is deployed, you don't need Python anymore. You don't need TensorFlow. You don't need PyTorch. So the runtime itself is self-containable. No other dependency needed, which is fine. In Python, just to give you some, I didn't plan to go very deep into that, but just a snippet of code with the famous iris dataset. I train a random classifier here, so you know that code, at least 40 of you. Then you convert, and there is, one simple function called convert scalar. We may change it to something more explicit, but today that's its name. You get a file, a single file, and you write it on your hard drive. Then the last part of the script may happen somewhere else. Doesn't mean because it's on the same slide, it's on the same machine. You could do it on Linux, Windows, ARM, whatever. Raspberry Pi, I'd like to see it because Raspberry Pi has Python, so it should be possible. And you load your file. You get, here I'm going to show what it means on an example, but basically it works. You load the file, and you run your prediction. More in depth, so your left side, you have the scikit-learn pipeline. And on the right side, you have the ONNX pipeline. It's a little bit more complex because we don't have, for each scikit-learn component, the exact ONNX component. Sometimes we decide that it's not necessary and we prefer to rewrite the scikit pipeline, the scikit-learn component into a series of matrix multiplication, matrix operation. But that's still a pipeline. So when you want to predict, you have input here, and you get output there. And here, if you have two outputs, just because it's a classifier, so you have the prediction and the priorities. But that's it. Basically, scikit-learn pipeline, ONNX pipeline, runtime, that's it. Some benchmark. So that's still a work in progress, so we don't cover every component in scikit-learn, but the plan is to cover most of it. And at least the more popular. This is just a benchmark for the Randomforest. The goal is to be faster than scikit-learn. So right now, if you have, let's say, Randomforest with 100 estimators, which means estimators, it's a term for scikit-learn, but 100 trees in your forest, I would say, I think it's the default parameters, but you are around 100 times faster than scikit-learn. For one prediction. Of course, if you run 1,000 prediction, scikit-learn is going to be faster. But that's the scenario. You are on a web service, you call Python code scikit-learn, you comes back with the prediction. If you replace the scikit-learn part by ONNX, you're on this, for this model, 100 times faster. For deep learning, I just took, so you have many models already converted in the ONNX format. So if you look on a web search engine, ONNX Zoo, you will find, for example, YOLO, which I like because I don't have to install YOLO to use it now. MobileNet, SqueezeNet, so basically the most popular one. And you can see ONNX is still faster for those models. It's for CPU, so I don't compare GPU to CPU. That's on the same machine. Work in progress, just to tell you that if you want to try now, don't send me an email saying that you're disappointed because it didn't work. That started a year ago. Scikit-learn is 10 years old, almost. So, but the plan is to be, I would say, in a very good shape in a couple of months. So let's say June or May. Right now, in every release, you have so many improvements that the API could change. It's not maybe not stable enough if you want to use it directly in your web service. But in a couple of months, everything will be in a very good shape. And for example, ONNX runtime was released 2 months ago. 2 months ago, in open source world, it's young, very young. And it's in active development, so you can check on how many pull requests I create per day. You can check that if you want. You can follow me. You can review the pull request. You can do many things.
Okay. Thank you very much. Yeah, you can join me here, Xavier. So it's time for questions. So if you have any questions, raise your hands. So one over there. So.
Thank you. I'm Jean-Patrice from Data Valoris, and we are providing optimization of neural networks after learning. And I would like to know, because we are building connectors for Keras, for TensorFlow, and so on, and I would like to know how Microsoft can help me to build an ONNX connector and even use your runtime.
You can contact me. I think it's the most simple answer I can find. In fact, it's working.
Yeah, it's working.
Okay.
Yeah, it's working.
The team I'm part of is spread all over the world. You have somebody in Australia, many people in Redmond, of course, in San Francisco, and some people in France. And I would be the best one to help you if you need that. So I didn't give my email, but I think there will be some toast.
Just a quick question on my side regarding the runtime. Does it work everywhere? Which means if I want to deploy it in some kind of IoT project on devices, is there any constraint or is there any specific implementation to run it in low power device, for example, or battery constrained device, or it's not the purpose of ONNX?
I wouldn't say there is a limitation today. I would just say we tried on Linux, of course, Windows and ARM. After that, I think there is other runtime. There are other runtime. You should check on ONNX page. So I'm more knowledgeable about ONNX runtime, obviously, but on the main page you will have many other runtimes, and maybe in the future, and I think it's already started, the people building such devices will come up with a runtime, dedicated runtime for ONNX, because ONNX is just a format, so you can it's a standard.
It's a question of implementation. What you're saying is
yeah,
you could implement it for a device purpose, for example.
Exactly.
I mean, okay, or IoT purpose.
Yeah,
but it's not the case today.
We're working actively, but we cannot work on everything. Okay. So give us some time.
Okay, question over there.
Hi, Emmanuel Dogera, Basic. What's your business model, and how does ONNX contribute to Microsoft's business model? Do you run it on Azure or other kind of services which will be related to your business somehow?
So first, I would not be the best person to describe what the business model is about that, because it's first it's brand new. So I think the business model is still to be written. But if you look on the documentation, the tutorials, you will see many examples saying how to use ONNX on Azure. And so obviously that's the goal.
Any question? So another on my side, you're saying that there are today different runtimes. So is there, if I have to choose between one runtime and another one, you said you can go to the website and there are a list of runtimes available there. But how do I choose the one which is going to be the one which fits the more to my project or to my constraints?
I think you have two components. The first one is obviously speed, because that's the first goal. And the second one is the coverage. If you have a pipeline with many components, you will need a function in your runtime implementing that component. And if you could even use two runtimes, one for the deep learning model, for example, and another one for the feature engineering. And I guess the only one addressing specifically feature engineering, it's ONNX runtime right now. I didn't remember seeing, in fact, all of them are mostly related to deep learning. The most, I would say, agnostic one is ONNX runtime, because one of the targets is to implement also standard machine learning. So if you don't want to switch, I think you get pretty good performance with ONNX runtime, and you will have only one runtime to install.
Yeah, question over there.
Thanks. If we have custom parts of our scikit-learn pipeline and that are custom made, do you expect us to build an ONNX function doing that with the few of the operators that you listed, or?
So that's one of the slides I prepared for that. So basically, I don't know your model, so I won't implement a converter for you. The goal is to have the runtime be able to run your model, and the trick is how do you convert your model into ONNX. Once it's in ONNX, you can be sure that the runtime will be able to run it. So the difficulties comes to into the conversion. And so I started to write something about the library I'm working on to make that easy. And here, that's the code for a custom transformer using scikit API. And here, if you go there, that's your function. Basically, your transform, it's just a scalar. And here, I'm trying to express it with ONNX. So div, sub are ONNX functionalities. And every time you use it, behind the library will know which ONNX operator to use here. So if you can, so basically what I do every day is I have a model. I write the ONNX function, then I test it with the runtime and check that I get the same predictions. Once it's done, you can plug your transformer in every pipeline. It's going to work.
Okay, Xavier. Very interesting, very technical, but very interesting. No, I mean, it was the purpose of this presentation, so thanks a lot. You can contact directly Xavier, and probably will be there also during the cocktail. So if you have other questions, you can meet with Xavier later. So thanks a lot, and now we are going to welcome on stage Chloe.